Good afternoon. My name is Bae Lee. I am PhD student from the Department of Ocean System Engineering. The topic of this presentation today is graph representation learning for sound event classification. Machine learning models based on graphs are primarily used to learn diverse graph structure data in various applications, such as chemistry, recommendation systems, and social networks. Graph neural networks, including the graph convolution neural network and the graph attention network, have been studied to efficiently learn information implied in the graph through a message passing process. Recently, GNNs, known for extracting features from non-Euclidean spaces using a minimal number of learning parameters, have been explored for learning image data without a predefined graph structure. GNS designed for learning time-varying graphs such as spatial-temporal GCN, SPGCN, and temporal GCN, TGCN, have also been studied for traffic forecasting. These GNS learning time-varying graphs utilize GCN to extract features from the graph at each time sequence and capture temporal correlations through networks designed for learning sequence data, such as recurrent neural networks, RNN. Recently, GNS have been explored for learning sound data. One approach represents the features of each time sequence as individual nodes, which are then connected to adjacent sequences. Ad- Additionally, sound has been graphically represented by dividing regions based on intensity levels in spectrograms obtained through short-wave transform and connecting overlapping regions. These graph representations, however, may encounter limitations due to potentially unnecessary or insufficient connections during the message passing process in GNS. Consequently, recent studies have focused on graph learning models that represent sounds in graph form. Nevertheless, these models, which assume a uniform adjacency matrix for all data, may not efficiently represent diverse sound sources and their temporal variations. This study proposes a graph learning model that represents sounds using a spectral graph S graph and a temporal graph T graph for classification. This model assigns each frequency bin in the spectrum generated by SDFT as a node and learns adjacent matrices over time to represent the S graph. Subsequently, features for each time frame are extracted from the S-graph using GCN, while the adjacency matrix of the T-graph is learned by capturing correlations between the extracted features. To learn adjacency matrices of the S-graph and T-graph, we use a simplified attention network as shown in figure. The professional model can represent each sound data as an individual graph with distinct adjacency matrices. Furthermore, it efficiently learns time-varying S-graphs without relying on traditional sequence data learning networks by utilizing the T-graph. The model is trained with the spectrum of the sound X, which consists of n frequency bins and n time frames. First, the model represents the S-graph G S, N. This S-graph consists of the node matrix HSN and the adjacency matrix ASN derived from the S. The HSN represents the nth matrix of the feature of tensor form. The feature of tensor form is derived by expanding the dimensions of X through a convolution operation with zero padding, as shown in the first equation. The ASN is generated by capturing correlations between node vectors in HSN via attention network. This attention network is a simplified model of a multi-head attention network primarily used in natural language processing fields. The attention network derives the matrix Q s, n from the node matrix H s, n via multiple linear transformations. Subsequently, the adjacent matrix A s, n of the weighted undirected graph is obtained using the scaled dot product attention mechanism. Finally, the NS graphs obtained are fed into N parallel GCNs to extract spectral features. These GCNs then perform node embedding as shown in the first equation. Then the graph feature vector is obtained by applying sampling to the embedding node matrix as shown in the last equation. The T-graph comprises the node matrix HT and the adjacency matrix AT. The HT is obtained by concatenating the spectral features expected over time. The AT is generated by capturing correlations between the spectral features over time, utilizing the attention network as shown in the second equation. The obtained T-graph is fed into GCN to extract temporal features. Then the graph feature vector is obtained by applying sampling to the embedded node matrix. Then we analyze the graphs represented by the proposed model with two examples. The proposed model is trained for binary classification utilizing simulated spectrogram data. The S-graphs feature self-connections at individual frequencies and interconnections among harmonic frequencies within the time frames, where these harmonics are present, highlighting the frequency relationships in spectral data. On the other hand, the T-graphs exhibit self-connections at individual timeframes and interconnections between timeframes where harmonies are detectable. These structural characteristics of the S-graphs and T-graphs enable the GCNs to efficiently extract significant features pertinent to sound characteristics. To evaluate the effectiveness of the proposed graph learning model, we implement it on publicly available sound event data sets, specifically urban sound AK and CBR dataset. Additionally, we established comparison baselines using traditional deep learning models, which include CNN, RNN, and convolutional recurrent neural network (CRNN). This table presents the averaged classification accuracies for each sound event in the urban sound AK dataset, along with the number of learnable parameters for each implemented model. The proposed graph learning model demonstrates higher classification accuracy by 4.2% compared to the CRNN, while requiring over 3 million fewer learnable parameters. Additionally, the proposed model exhibits fewer learnable parameters than both the CNN and RNN, with at least 70.3% higher classification accuracy. This table shows the averaged classification accuracies for each shift type in the severe data set, along with the number of learnable parameters for each implemented model. The proposed model shows a higher classification accuracy by 2.5% compared to the CRNN, while requiring over 3 million fewer learnable parameters. Additionally, the proposed model exhibits fewer learnable parameters than both the CNN and RNN, with at least 6.8% higher classification accuracy. First law figures illustrate the adjacency matrices of the S-graphs and T-graphs derived from the spectrogram of the dog-bark class in the urban sound AK dataset. The adjacency matrix of the T-graph represents correlations between different time frames in which sound events occur. Similarly, the adjacency matrices represents correlations between frequencies using weighted connections. These weights are determined based on the intensity of frequencies within specific time frames that coincide with the occurrence of the sound event. Second row figures show the spectrogram of the potable sound from the severe dataset along with the corresponding S-graphs derived from this spectrogram. The spectrogram reveals a characteristic pattern where high-frequency harmonics progressively diminish over time. Consequently, the S-graphs gradually exhibit a ligous association with high-frequency harmonics. This conclusion page. In this study, we introduced the graph learning model that employs GNS, known for their efficiency in feature extraction with few learning parameters, to the domain of sound data learning. The proposed model facilitates the implementation of a lightweight classification model characterized by a minimal number of learning parameters. Additionally, the architecture of this model can be applied to a wide range of datasets, even those lacking a predefined graph structure. While the model demonstrates superior performance for the validation using various of data set is an essential step for future research. Thank you for your attention. If there are any questions, I will do my best to answer them.